Okay, today talking about how to use the calculator to find to answer questions about the probability, the normal distribution. Okay, normal PDF. That's the probability density function. This is the probability of a single value of a random variable x. We don't use this one very often. Basically, it's like one thing happening. Like if you had a test and the mean was 85 and the standard deviation was 5, it'd be like, what's the probability that a student selected at random would have gotten an 83? Okay? The normal CDF is a cumulative distribution function. This basically returns the cumulative probability from 0 up to some input value of the random variable x. And basically, it's like, what's the probability the student got at least an 83? All right. It returns a percentage variant or a continuous distribution curve from negative infinity to the x. You can set the lower bound at 0. All right. And some of you have the new calculators, and instead of having that place to put in a lower bound, it already starts with a lower bound, maybe of like 99e to the negative 100. All right, that's basically like 0.0000000000099. All right, but I like to just use 0. All right, if I'm doing from 0 up. If I wanted to know greater than the value, like probably somebody scored greater than an 85, then I would take and have the lower bound of 85, the upper bound. I would put in like, I don't know, 99,999. Something. It's essentially going to infinity. All right, 100 is the highest score possible, but you want to make sure you're including all of the possibilities there. All right, so you want to go up beyond that. All right, and then you put the mean and the standard deviation. Inverse norm. This is where you can actually take a score. You can actually take a probability, which is the percent, as a decimal, and the mean and standard deviation, and it will give you that score. That's kind of how you can do a percentile rank with a. That's how you can do a percentile with a normal distribution. Let's get into the first example here. Right, example 1. Given a normal distribution of values for which the mean is 70 and the standard deviation is 4.5, find the probability that the value is between 65 and 80 inclusive. Okay, so I've got normally distributed, and my mean is 70, and the standard deviation is 4.5. Okay? All right, so this is going to be like 74.5, this is 79, this one is 83.5. And then going down this way, this is 65.5, this is 61, and this one is going to be 56.5. Okay, like that. All right, and then of course remember you got the halves if you were doing the percent. If I was going to use the curve, I would kind of be bounded to these values. All right, and that's how I can kind of find the exact. But with the calculator, I can do something more. All right, so I want to find the probability that something is between 65 and 80. All right, well, the way to do this on the calculator is, let me pull this up, and you'll see right here the vars button over here. If you hit the second vars, that second variables, that goes to distribution. All right, now I'm looking for the probability between two numbers, so that's going to be a cumulative kind of thing. So I'm going to do normal CDF, all right, and then my lower bound goes first, 65, comma, 80, comma, and then I always end with the mean and then the standard deviation every single time. I end with the mean, comma, the standard deviation, 4.5. Close that parenthesis and enter. And there we go. All right, so the probability value is between that, and that is 0.8536. All right, so 0.8536, and we'll say like 0.85. All right, probability value is greater than or equal to 75. So again, this is going to be a cumulative thing. It's going to be all these scores that are like 75 and larger. So it's all of this over here. All right, now if it's at 74.5, I could just go right to the graph and count up my percents. All right, but since it's 75, it's just a little bit bigger than 74. So I go to second vars, which is the distributions, all right, and then I'm going to go to a normal CDF, all right. Now this time my lower bound is 75, that's my low score, and this is going up to infinity, right? Well, I'm just going to put in 99999, you know, just like a big number like that, all right? It doesn't matter exactly what number you use, just make it a large number, okay? And then you end every time with the mean and then the standard deviation. Okay, there we go. So the probability somebody is scored greater than or equal to 75 is 0.13326, so we'll say, about 0.13. Okay, now it's probably the value is less than 62. So less than 62, I mean, if I come back and refer back down to here, 62 is like around in here, right? And that's all this area, right? All right, so anything less than 62 is going to be, again, normal CDF. All right, now I need a lower bound, all right? I'm just going to go 0. Just can't get lower than a 0, right? You can, but I mean, we're talking about like test grades here. 0, 62, the mean was 70, and then the standard deviation is the last thing. Always end with the mean and then the standard deviation. All right, so 0.037, so, you know, about 0.04 for that one. All right, now to find the 90th percentile for this distribution, this is actually an inverse norm. All right, it's giving you the probability, and you have to find what is at the 90th percentile. So basically, you could go up and count the percents and figure out where 90% is, or you can hit second, and then I see choice 3 is inverse norm, okay? And what I need to do is I need to put in 0.9, okay? Because I need to put it in as a probability. I don't put it in as a percent. 0.9, comma, 70, comma, 4.5, enter, and that's the score right there, 75.76, right? So 75.77, all right, something like that, okay? There we go. That's how you can kind of use your calculator, all right? You can use your calculator to answer those questions. All right, next. I wasn't sure if I was going to present this or not, but it is one of our standards, so I'm going to kind of go through it relatively quickly. And this is the case where I want to use a normal approximation for a binomial distribution, okay? And just to refresh your memory, let's do a binomial probability here. Probability that someone gets divorced by the age of 30 is 1/5. Probability that of 50 people who got married, exactly 8 of them will be divorced by 30. So that's going to be an NRPQ. All right, Nina runs pretty quick, whatever it is you used to remember that. And we have 50 people total, and I want exactly 8 of them to be divorced by the age of 30. The probability that you're, I guess in this case, we're going to consider being divorced a success, unfortunately. All right, the age of 30, probability you get divorced by age 30 is 1/5, so P is 1/5, and then Q has got to be 1 minus P, which is 4/5. Okay, and then that's going to be 50C8, 1/5, raised to the 8, because we want 8 of them to get divorced, and really we want 42 of them not to get divorced. There you go. All right, and then you can evaluate that. Now if I wanted to do at most 8 out of 50, okay, I can do it, but I have to do it for R equals, right, and RPQ. I mean, it's going to stay the same. The n's the 50, the P is 1/5, and this is 4/5. But then you'd have to do 0, 1, 2, 3, 4, 5, 6, 7, and 8. All right. So that's quite a bit of work to do there. All right. And what we can do is we can use the normal curve to approximate this binomial probability. And I'm going to scroll down to the bottom of the page first, because certain times this is appropriate and certain times this isn't. Okay. You can use a normal approximation for a binomial probability when NP has to be greater than or equal to 5, and N times Q also has to be greater than or equal to 5. All right? So, you know, if I go back up to my example here, that would be 50 times 1/5, which is 10, and 50 times 4/5, which is 40. And those are both greater than 5, so it would be appropriate to use this normal distribution. Okay? couple things. N, that's still going to be the number of tries, right? Or whatever it is. And P is going to be the probability of success. And Q is still the probability of failure. All right, and then I've got another symbol here, a new symbol. It's called mu. All right, that's kind of the same thing as X bar, but that's going to be the mean. All right, and then sigma, that's the standard deviation. The problem with binomial probabilities compared to a normal distribution here is that binomial probabilities are discrete. Right? It's like 8 people, then 7, then 6. You can't have like 7.5 people get divorced. All right? It doesn't work that way. So what I have to do is to turn this like continuous thing almost into a discrete thing is I just have to kind of include like a plus or minus 0.5. All right? If I want to know the probability that 8 or more will get divorced, then I'm going to look at it from 7.5 and up. And if I want to look at it like 8 or less, then I'd look at it from 8.5 and down. So at most, 8 out of 50. All right, before I can do this, I need to figure out what the mean will be for this and the standard deviation. Okay, so my mean in this case is going to be, the mean is NP. All right, which in this case was, we had 50 people, and the probability that they got divorced was 1/5. So the mean was the mean is 10, and then the standard deviation is the square root of n times p times q. All right. So the standard deviation is the square root of 50 times 1/5 times 4/5. Okay. And when you do 50 times 1/5 times 4/5, you're going to get the square root of 8. Okay, square root of 8. Okay, 50 times 1/5, 10, 4/5 of that is 8. Yep, okay. So what about at most 8 out of 50? So at most 8 out of 50 is like 8 or fewer. So what I'm going to want to do, all right, is I'm going to want to use my calculator. All right, and I'm going to want to have normal CDF, right? And I'm gonna have like from 0 people up through. If I want at most 8, I gotta have that 8.5. All right, and then comma, and the mean, and then the standard deviation, square root 8. Okay, and you can put that in as a decimal if you want for that, or you can leave it in as a radical. Okay, let's give it a try. Second distribution, normal CDF, which is choice 2, and I am doing 0, comma, 8.5, comma, 10, comma, and then square root of 8. All right, here we go. And there it is, 0.2977. Now this is only going to be accurate to 2 or 3 decimal places. So what I'm going to do is I'm going to round this kind of appropriately. This would be 0.30, something like that. 0.30. Okay, there we go. All right, and another example here. 2% of smokers get lung cancer. What is the probability that in a random sample of 900 smokers, at most 18 of them will develop cancer? Okay, so the mean, you have to decide if this is going to be appropriate or not, right? So to use the normal distribution. So you have NP, all right, and then NP is equal to, we have 900 smokers and 2% is going to be 180. And then we have NQ, which is like 98% of 900, which is obviously greater than 5, 882. Okay, so that's okay. And then you know your mean here is 180. All right, to find you have to find your standard deviation. Okay, and the standard deviation is going to be the square root of 900 times 0.02 times 0.98. Enter. All right, and then I've got 4.286. 4.286.